Right now, NASA can show you a single rock sitting on the surface of Mars. Not a region, not a mountain range, a rock, 30 centimeters wide, sitting 63 million miles away from Earth, and they can show it to you in detail. Now, here's what I want you to do. Picture the ocean closest to you. Maybe it's the Atlantic. Maybe it's the Pacific. Maybe you live somewhere landlocked and the nearest coast is 1,000 miles away. It doesn't matter. Because right now, if you asked every scientist, every oceanographer, every navy, every space agency on this planet to show you what's sitting on the ocean floor directly below you, they can't. Nobody can. We have mapped less than 26% of our own ocean floor in any meaningful resolution. 26. And yet, we can show you a rock on Mars. That's not a political statement. That's not an exaggeration. That is the single most disorienting fact in modern science. And today, we're going to find out exactly why it's true and what it means for everything we thought we knew about this planet. Stay with me, because what comes next is going to completely change the way you look at the water. There's a number that oceanographers use when they want to make a point: 71. 71% of this planet is covered in ocean water. You already knew that. Everyone knows that. It's the kind of fact you learn in 4th grade and then stop thinking about entirely. But here's what 4th grade didn't tell you. Of all the water on Earth, all of it, every ocean, every lake, every river, every ice sheet, every droplet of rain falling right now somewhere over the Pacific, 97% of it is ocean water, not lake water, not river water, not groundwater, ocean water. This planet is not a rock with some water on it. This planet is an ocean with some rock sticking out, and we know almost nothing about it. Think about that for a moment. The dominant feature of this planet, the thing that makes Earth look blue from space, the thing that drives our weather, regulates our temperature, produces more than half the oxygen in every breath you take. We have mapped less than a quarter of it. If this were a country, it would be the equivalent of knowing what 3 of your neighbor's rooms look like and assuming the rest of the house is probably fine. So how did we get here? How does a civilization that can land a rover on another planet still not know what's at the bottom of its own ocean? That's what this video is about. And the answer is more complicated and more fascinating than you think. Let's start with Mars, because understanding what we did there helps explain everything. In 2001, NASA launched a spacecraft called Mars Odyssey. Its job was to orbit Mars and map the entire surface using thermal imaging and infrared sensors. It took about 1 Martian year, roughly 687 Earth days, to complete a full map of Mars. Today, thanks to Mars Odyssey, Mars Reconnaissance Orbiter, Mars Global Surveyor, and several other missions, we have maps of Mars with a resolution of about 5 meters per pixel. 5 meters. That means if something on the surface of Mars is larger than a small car, we can probably see it from orbit. Now let's talk about the ocean. You can't use satellites to map the ocean floor. Not directly. Water blocks the kind of electromagnetic radiation that satellites use to image surfaces. The ocean might as well be a wall of solid rock as far as most satellites are concerned. What we can do from space is measure tiny variations in sea surface height. Places where the ocean surface bulges slightly upward over underwater mountains because of gravitational pull, or dips slightly inward over deep trenches. That gives us a rough idea of what's down there. Very rough. The best global ocean floor map we have from satellite data has a resolution of about 5 kilometers per pixel. 5 kilometers. Compare that to 5 meters on Mars. That's a difference of 1,000 times. 1,000 times less detailed. At 5 kilometers per pixel, you could have an underwater mountain range the size of the Appalachians sitting down there, and it would barely show up as a smudge on the map. You could have entire valleys, plains, canyons, features unlike anything we've ever seen. And we wouldn't know. We wouldn't know. Now here's where it gets interesting. The solution to mapping the ocean floor does exist. It's called multi-beam sonar. You mount it on a ship, you send out pulses of sound, and you measure how long they take to bounce back from the bottom. It works incredibly well. When a ship runs a multi-beam sonar survey over an area, the resulting maps are extraordinarily detailed. Resolution of around 100 meters, sometimes better. 100 meters per pixel versus 5 kilometers per pixel. That's 50 times more detailed than anything satellites can give us. The problem is simple. To map the entire ocean floor at that resolution, you need ships, physical ships, moving slowly across the water, back and forth, row by row. The ocean covers 361 million square kilometers. At the speed research vessels typically operate, around 10 knots, and accounting for the width of a typical sonar swath, scientists have calculated that it would take about 600 ship years to map the entire ocean floor. 600 years of continuous ship time, all at once. If you had every research vessel on Earth doing nothing but ocean floor mapping starting today, it would still take decades. And here's the thing, we haven't been doing that. We haven't even been close to that. As of 2024, the Seabed 2030 project, which we'll get to in a moment, estimates that we have surveyed roughly 26% of the ocean floor at meaningful resolution. 26% in the entire history of human oceanography. You could fit everything we've actually mapped at good resolution into a shape smaller than the continent of Asia. Everything else is guesswork. I want you to picture something. Imagine you're standing in a completely dark room. You have one small flashlight. The room is about the size of a football stadium. Now imagine you have to map every single square inch of that room using only what your flashlight can illuminate at any given moment. That's ocean mapping, except the room is 361 million square kilometers, and your flashlight has to travel on the surface and send sound pulses down. And some parts of the room are 11 kilometers deep, and the pressure at the bottom is equivalent to stacking 50 jumbo jets on top of your head. That last part isn't a metaphor. At the bottom of the Mariana Trench, the pressure is about 11,000 pounds per square inch. Every piece of equipment that goes down there has to be engineered to survive forces that would crush a standard steel submarine like a paper cup. This is why ocean exploration is, in many ways, harder than space exploration. I know that sounds counterintuitive. Space is the final frontier. Space is the unknown. Space is where the danger is. But here's the thing. In space, there's no pressure. Vacuum is vacuum. You build something airtight and it survives. In the deep ocean, the pressure actively tries to destroy everything you send down there. Every depth increase makes the engineering challenge exponentially harder. We've sent humans to the moon 6 times. We've sent humans to the deepest point in the ocean exactly 3 times in history. 3. The first time was 1960. The second was 2012. The third was 2019. 3 times. In all of human history, the moon is 239,000 miles away. The bottom of the Mariana Trench is 7 miles down. 7 miles. And we've been there 3 times. If you've made it this far, I want you to stay with me. Because we've established the problem. We don't know what's down there. But the more interesting question is what we've found in the small fraction that we have explored. And some of it is going to completely rewrite what you think you know about this planet. If this is the kind of content you want more of, subscribe to Abyss Files right now. Every video we make goes somewhere most people have never thought to look. Now, let's talk about what we've actually found. When scientists do get detailed sonar data back from an unexplored part of the ocean floor, what they find consistently surprises them. Not occasionally, consistently. In 2023, a research team mapping a section of the Pacific Ocean floor off the coast of Chile found a seamount, an underwater mountain, that rises 4,000 meters from the ocean floor. 4,000 meters. That's taller than anything in the continental United States outside of Alaska. Nobody knew it was there. It wasn't on any map. It wasn't in any database. A mountain range taller than the Rockies, sitting in the Pacific Ocean, completely unknown until 2023. And that's not unusual. That's routine. In 2022, another expedition found an underwater canyon off the coast of New Zealand that rivals the Grand Canyon in scale.
Yeah, this is interesting. We see some pyramid-shaped structures. I can't really think of anything that jumps off the top of my head that would create features that look like this. Hopefully there are some geological folks on the line that might be able to have some sort of better idea of what could create this really distinctive looking feature. Ah, excellent. There we go. That's a nice chunk of this structure that we're getting right now. And it looks like we're getting some hole pieces inside. I'm looking at the chamber of our suction sampler right now. Yeah, and just really absolutely friable, very crumbly. Jason Chater of the USGS has weighed in to tell us a little bit about them, which is awesome. So these are mudstones or clay stones. So it's the product of the hemipelagic sedimentation that you've been seeing here so far. These samples have been largely dewatered by compaction. So basically just the weight of the sediments itself has squished the water out between them, resulting in that really densely packed area. So this is probably an erosional feature that was just happened to be carved into this really distinctive, interesting looking shape.
The Grand Canyon is 446 kilometers long. This underwater canyon system was comparable in length. Nobody had ever seen it before. Think about what it would mean if we discovered a canyon the size of the Grand Canyon somewhere on land. It would be international news. It would be one of the great geographic discoveries of the century. We find things like this in the ocean regularly, and most people never hear about it, because most people don't realize we didn't already know. That's the trap. We assume that because we know the ocean is big and deep and mostly unexplored, we have some general sense of what's down there. We don't. The ocean floor is not a flat plain of mud with occasional trenches. It is, and I want you to really hear this, the most geologically complex surface on this planet. The mid-ocean ridge system alone, the underwater mountain range that runs along the bottom of every major ocean, is the longest mountain range on Earth, 65,000 kilometers long. That's 1.5 times around the equator. And most of it has never been directly observed by human eyes. Here's something that will permanently change how you think about this planet. The tallest mountain on Earth is not Mount Everest. If you measure from base to peak, the tallest mountain on Earth is Mauna Kea in Hawaii. From its base on the ocean floor to its summit above sea level, Mauna Kea rises 10,210 meters. Everest is 8,849 meters from sea level to summit. Mauna Kea wins by over a kilometer. You just couldn't see the bottom half because it was underwater. Now here's the question that should be keeping oceanographers up at night. If Mauna Kea was hidden for most of its height by the ocean, if we almost missed the tallest mountain on Earth, what else are we missing? What other Mauna Keas are sitting down there right now? Bases buried in darkness, peaks a few hundred meters below the surface, completely invisible to every map we've ever made. The answer, based on what we know about seamount distribution, is probably thousands, tens of thousands potentially, underwater mountains we haven't seen, haven't named, haven't studied, just sitting there, in the dark, waiting. Let's talk about the Seabed 2030 project, because this is the most ambitious ocean mapping effort in human history, and almost nobody knows it exists. The goal is simple: map the entire ocean floor at meaningful resolution by the year 2030. It was launched in 2017 by GEPCO, the General Bathymetric Chart of the Oceans, and the Nippon Foundation of Japan. When they started, roughly 6% of the ocean floor had been mapped at high resolution, 6%. By 2024, they had reached approximately 26%. Progress is accelerating. New technologies are helping. Autonomous underwater vehicles, improved sonar systems, data sharing agreements between countries that used to keep their surveys secret. But they're still racing against the clock. 26% in 7 years. They need to reach 100% in 6 more years. The math is difficult. And here's the uncomfortable truth that project scientists have started to acknowledge publicly. They're probably not going to make the 2030 deadline. Not because they're failing, but because the ocean is simply too large and the technology is still too slow. What they will achieve is still extraordinary. They'll have mapped more of the ocean floor in a decade than humanity mapped in the previous century. But complete, full resolution, every square kilometer, probably not by 2030, maybe not by 2040, maybe not in our lifetimes. Black screen, 3 seconds. We might live and die on a planet whose surface we never fully see. I want to take a step back for a moment and ask a question that doesn't get asked enough. Why does this matter? Who cares if we've mapped the ocean floor? The fish down there don't care. The rocks don't care. Why should you care? Here's why. The ocean floor is not passive geography. It's not just scenery. It is an active geological system that directly controls what happens on the surface of this planet, including where you live. 90% of all earthquakes happen along tectonic plate boundaries. Most of those boundaries are underwater. Every major tsunami in recorded history started with an underwater geological event: a fault slip, a submarine landslide, a volcanic eruption on the ocean floor. In 2004, the Indian Ocean earthquake and tsunami killed approximately 227,000 people. The fault that caused it runs along the ocean floor. We had never mapped that section of the floor in detail. We still haven't fully mapped it. This is not abstract. This is not academic. Knowing what's on the ocean floor could tell us where the next great earthquake is most likely to occur. It could give coastal communities around the world more warning time. It could save lives. And that's before we get to climate. The ocean drives this planet's climate system. Ocean currents move heat from the equator to the poles. The chemistry of the deep ocean influences atmospheric carbon dioxide levels over timescales of centuries. But we can't fully model those systems because we don't know what the ocean floor looks like. We're trying to understand a machine without knowing what most of its parts look like. That's where we are. Let me tell you about hydrothermal vents, because this might be the most important thing I say in this entire video. In 1977, a research submersible called Alvin was diving along the Galapagos Rift, a section of underwater volcanic ridge in the Pacific, when the scientists on board saw something that should not have existed: warm water rising from cracks in the ocean floor. Not just warm, hot, and around those vents, in water that had never seen sunlight, that was thousands of meters below the surface, where by all conventional scientific understanding, nothing should be able to live. Life, tube worms 2 meters long, giant clams, shrimp, crabs, fish, entire ecosystems, thriving in complete darkness, sustained not by photosynthesis, but by chemosynthesis, by microbes that convert the chemical energy from the vent water into food. An entire branch of life that didn't need the sun. Before 1977, scientists believed, genuinely believed, that all life on Earth ultimately depended on sunlight. That photosynthesis was the foundation of every food chain on the planet. That belief was completely, fundamentally wrong. And we only found out because someone happened to point a submersible at a random section of ocean floor. Think about what that means. If a discovery that rewrote the foundational theory of life on Earth was sitting in the ocean, undiscovered, until 1977, what else is down there? What other foundational assumptions about life, about geology, about chemistry, about this planet are wrong right now? Sitting in the 74% of the ocean floor we haven't mapped, waiting for someone to accidentally stumble across them. We don't know. That's the honest answer. We don't know. Here's something that will sit with you. The deep ocean is the largest living space on Earth, not by area, by volume. When you factor in depth, the ocean represents about 99% of the living space on this planet. Every forest, every jungle, every prairie, every city, every farm, every place where any land animal has ever lived. All of it combined represents about 1% of Earth's available living space. The other 99% is ocean. And in that 99%, we have catalogued roughly 250,000 species. Scientists estimate the actual number could be anywhere from 500,000 to 10 million. 10 million species potentially living in the ocean. We have found roughly 250,000 of them. At current rates of discovery, it would take centuries to catalogue everything that might be living in the deep ocean. Centuries. And that's if nothing new evolves in the meantime. Which of course it will. Life doesn't wait for us to catch up. Let's come back to Mars for a moment. I don't want you to walk away from this video thinking we wasted money on space exploration. We didn't. Mars mapping has given us extraordinary insights into planetary geology, the history of water in our solar system, the conditions under which life might exist elsewhere in the universe. It is genuinely important science. But here's the comparison that matters. The total budget for NASA's Mars exploration program between 2001 and 2020 is approximately $11 billion. The total annual budget for NOAA, the National Oceanic and Atmospheric Administration, the main US government agency responsible for ocean research, is approximately $6 billion. Per year, yes. But of that $6 billion, only a fraction goes toward ocean floor exploration and mapping. The Seabed 2030 project, which aims to map the entire ocean floor, operates on a budget of tens of millions of dollars per year, tens of millions, to map the dominant feature of the planet we live on. This is not a critique of space exploration. This is a statement about priorities. We chose to know Mars. We chose that. And we deprioritized knowing our own planet in the process. That is a choice. And we are living with its consequences every day. I want to tell you about something that happened in 2015 that almost nobody remembers. A team from the Schmidt Ocean Institute was conducting a routine survey of the ocean floor near the Mariana Trench when their sonar picked up an enormous feature they hadn't expected: a plateau, rising about 2,000 meters above the surrounding ocean floor, roughly the area of the state of Colorado. It had never been mapped before, never been named, never appeared in any scientific literature, a feature the size of Colorado, on the floor of the most studied ocean in the world. Routine survey. That's how unexplored the ocean is. Routine surveys find things the size of Colorado. And that same year, 2015, we completed the highest resolution map ever made of Pluto. Pluto, a dwarf planet 3 billion miles from Earth, smaller than our moon, visited exactly once by a spacecraft that took 9.5 years to get there. We have better maps of Pluto than we do of most of our ocean floor. Pluto. I'll let that sit for a moment. Now, I want to talk about what comes next. Because the story doesn't end with us being ignorant and helpless. Technology is changing this. Autonomous underwater vehicles, AUVs, are becoming cheaper, more capable, and more reliable. Instead of needing a research ship to constantly supervise a mapping mission, you can now deploy fleets of AUVs that operate independently, covering far more ground. In 2022, a team from Woods Hole Oceanographic Institution demonstrated that a coordinated fleet of AUVs could survey an area of ocean floor in days that would have taken a single ship weeks. Machine learning is also transforming how we process sonar data. What used to require months of manual analysis by trained scientists can now be done in hours by algorithms trained to recognize geological features. And there's a relatively new approach called satellite-derived bathymetry, using very precise measurements of sea surface variation to infer more detailed ocean floor topography than was previously possible. None of these technologies solve the problem completely. The ocean is still too vast and too deep for any current technology to fully map in the near future. But the trajectory has changed. In 2017, 26 years after the Seabed 2030 project's baseline was established, we had mapped 6% of the ocean floor. 7 years later, 26%. If that rate continues to accelerate, and the technology suggests it will, we might reach 50% by the early 2030s. 50%. Not complete, not even close to complete, but more than we've ever known. More than any generation of humans has ever known about this planet. I want to end with something that I think matters more than maps and percentages and budget comparisons. Somewhere on the floor of the ocean right now, there is something we have never seen. Not a new species of small fish, not a slightly unusual rock formation, something genuinely unprecedented, something that, when we find it, will change the way we understand this planet, or life, or perhaps both. I say this not as speculation, but as statistical certainty. Every time we go somewhere new in the deep ocean, we find something that surprises us. Every single time. The hydrothermal vents rewrote the theory of life. The methane seeps introduced us to entirely new biochemical systems. The deep ocean microbiome, the microscopic life living in sediment kilometers below the ocean floor, contains more genetic diversity than exists in all surface life combined. Every single time. We go somewhere new. We find something extraordinary. And we've only gone somewhere new in about a quarter of the ocean. 3/4 is still waiting. 3/4. You are living on a planet whose greatest feature remains almost entirely unknown to you. Not because we lack curiosity, not because we lack intelligence, but because it is genuinely, deeply, extraordinarily difficult to get down there. The ocean keeps its secrets behind walls of pressure and darkness and sheer scale that dwarf anything we face in space exploration. And yet, piece by piece, survey by survey, dive by dive, we are learning. And every single thing we learn tells us the same thing. We were wrong about the shape of the floor, wrong about the nature of life, wrong about what exists down there, wrong about how much we know, completely, fundamentally wrong. And that wrongness, that humbling, disorienting, beautiful wrongness, is the most exciting thing about the ocean. Because if we were this wrong about what we know, think about what we haven't found yet. If this video made you see this planet differently, even slightly, then this channel is for you. Abyss Files exists for exactly this. The stories that don't make headlines, the science that rewrites what we thought we knew, the parts of this planet that most people will never think to look at. Subscribe, turn on notifications, come back for the next one, because we're just getting started, and the ocean has a lot more to show us.